Okay, so yeah, we were looking at monadic second order logic over words, and in order to interpret this formula, we were talking about structure. So a structure has essentially these three things, like a domain and a uh, signature and an interpretation. So the domain, as we said, for the word model, is the position of words, and the signature will have the predicates and essentially the predicate symbols, and that also includes like the arity of the predicate symbols, like the less than has an arity of two, it's a binary predicate and so on. And I is the interpretation, it gives meaning to these predicate symbols. And we also discussed about free variables and bound variables. So a free variable uh, is one which is not bound by a quantifier, right? So essentially, the meaning of a bound variable directly comes from the quantifier, whereas for the free variables, we need to add separate valuations, right? And so if we have like for the MSO formula, like if these are the free variables, so these are the second order variables, these are the first order variables, we need to add in addition these valuations, right? And then we can say, well, given these valuations, whether this formula is satisfied or not, and so on. So we looked at some examples and sentences where essentially formulas without any variables, so you can directly interpret them over the word models. And we also talked about MSO definable language. So essentially, this is MSO definable, a language L, which is a subset of sigma omega. It's MSO definable if and only if this L equal to L of phi for some MSO formula phi. What was L of phi? It's a set of words which satisfy the formula phi. And similarly, you can also define FO definable language for an FO formula phi. Good. And we also discussed something called an extended word model. Like if the formula has three variables, then we would have like this kind of models. And we say that for every position j, we would record if j equals k1 to km or j belongs to this capital K1 or capital K2, capital K, like that. So this was an example, like here you have small k1 equal to 2 and these two uh, second order variables, capital K1 and capital K2. And we said like since k1 equal to 2, we have here a 1 and in the rest of the places you have zeros. And capital K1 is 2, 3, 4. So we have ones here, and similarly capital K2 is 1, 4, 5, 6, like you have the ones here. Okay, so that is the thing. We also looked at some more examples. And then today we are going to look at the Büchi's theorem, right, which is the characterization. So it says that a language is omega regular if and only if it is MSO definable, right? So we would have two directions. One direction is, so given an NBW, we should be able to construct a formula in the MSO logic that we have seen, and vice versa. Given a formula, we should be able to create NBW, right? So let's first look at this direction from automata to logic, right? So what we would like to do in order to capture the set of words which are accepted by this automaton using a logical formula, essentially we'll try to encode an accepting run in this logic. Okay, we would like to encode an accepting run in the logic. So now here, for example, in this automaton, so there are three states, right? And corresponding to each state, we are going to have a set variable like an xi, a set variable xi, which will have a set of positions as we saw earlier. And what would these positions denote? Any idea what would these positions denote? Corresponding to each state, I have a set variable xi. And I'm saying, what did I say? I said that we would like to encode an accepting run in the formula.
Will
Right.
it be like it's reaching that state infinite?
Well, so I'm saying that this xi, it corresponds to some state qi, right? And if you're talking about a run, xi, capital Xi will have a set of positions. So what positions do you think, like in the run, that will correspond to the state and so on, like in an in a
That position is in that particular.
exactly that position in that state, right? So that's what it's going to denote. This set will have all the positions such that the run is in that state in these positions, right? So that's what. So, right. So I'll just write this. So we have set variable xi for each location ui. This would denoting the positions at which the run of the automaton is in state qi. Okay. And the idea is that describe in this formula, describing this logic MSO, the constraints over these variables, right? Constraints that some x, so if you have, let's say, k states, x1 to xk, and suppose your alphabet is A and B. So we saw this PAPB, these things, right? Should the constraint that these sets should satisfy corresponding to an accepting run. Clear? So this is the idea. Okay. So in MSO, we are going to define the constraint, describe the constraints such that these sets x1 to xk and PAPB, this should satisfy the constraints corresponding to this accepting run. Okay. So again, what are we doing? We are trying to construct a formula which will encode an accepting run. And as you say, these sets x1 to xk corresponding to states q1 to qk, they will have the positions such that at that position, the run is in that state, right? Good. So now, let's say, just to give you the example, give you an example. Say I have a word corresponding to this automaton. So the word is of this form AA, BB, AB, A omega. So of course, this word is within the language, right? Because this automaton accepts some word which has two consecutive B's, right? So you have AABB, AB, A omega. So this word is in the language, and we would like to have this encoding, right? So you have, let's say, there are three states, and corresponding to these, we have these three sets, x1, x2, x3. And how should an accepting run look like? So you have corresponding to the first is, you just take the self loop here, right? And then you have the B here, the next B here, and then AB, A omega, you take the self here, right? So one thing here to know is that it's like when I'm reading this first A, before reading this first A, where I am located. So that's what we are looking at, right? Before reading that letter, where I am, in which state I am, right? So before reading this letter A, I am in the state Q1. So then I'll have a 1 here, right? Then when I read the next, before reading the next day, so after reading the first day, before reading the second day, I am here. So I'll put a 1 here. Before reading the first B, I'm still in Q1, right? So I'm here. So after I read the first B, before reading the second B, I am in state Q2. So I have a 1 here. And after reading the second B, right? Before reading this, I am here. And then I continue to be here, like this, right? So this is how my sets will look like, x1 to xk. This sets will look like. Okay. So now, in order to encode an accepting run, what are the things that I should have? Like, so just to see, like the properties that a run should have in terms of the constraints we are talking about, this in terms of these sets. So one thing is that at any time, a run is exactly in one state, right? At any point, a run at any point, say a position, it cannot be in multiple states at the same time. Clear? So it should be at any one state, right? So if you have a position, let's say the position should be in a unique, set, correct? So this is one thing. Secondly, what is the other thing we can say? If, for example, like the initial position, right? The initial position should be in one of the initial states, right? It should be in one of the states which corresponds to one of the initial states. So this is another condition. What other conditions we may need for an accepting run to encode?
The one of the final state should come infinitely.
Sure. Sure.
In
That
this
is one
case,
thing.
X3 should be
Yeah. And what else do we need to define a run?
transition should be valid.
The transition should be a valid transition, right? So whenever you are going from, let's say, like you have consecutive positions, say small x, small y, and small x is in capital Xi and small y is in capital Xj, then there should be a transition from Qi to Qj, right? And suppose the letter that you are reading is A, then at that position, it should be, that position should also belong to the set PA. Okay, so this is what exactly these conditions we are going to encode now, right? So the first one is that the Xi is partition the set of positions. The automaton is in exactly one state for each position, right? So how can I write this? Can you tell me the formula?
Like you can put an or, and then in each thing it will be x.
Correct.
And not xj.
Sure. Very good. So I'll say for all x, for every position x, there exists capital Xi such that Xi of x and what is that?
Not xj. Okay.
Ah,
For all j not equal to.
yeah. So this is actually a conjunction, right? So it should not be an or, but so j not equal to I, this is what it is, right? So you are in some set and exactly in one set. You cannot be in multiple sets at the same time, right? What about the second one? At the first position, it's in an initial state, maybe rather than saying the initial state, it's in an initial state. How do you say this?
So X implies
Right.
X
Capital X
implies
not.
Implies
Do we know the set of initial state?
you can have a set of initial states, of
So
course.
then
Like,
there exists x, and then q. Suppose q is the initial state, q not capital X, and
so you can have like a set of
R's.
Q0, I call like a set of initial states, right? So then,
there exists capital X bracket Q naught capital X and capital X naught.
Uh-huh.
So I'm saying the state that I am in
Mm-hmm.
is there in Q naught and this first of X is there in the capital.
Okay. So, uh, okay. So I will say, suppose if I do this, uh, so you also need a quantification, like there exists a
XQI.
sorry, xi is for the index is just I'm writing an xi for qi.
Um,
Okay.
So we can't have sets of sets that stage. Like we can't say Q naught is the set of all.
Sorry.
We can't say Q naught is the set of all initial state sets. Like
Q naught is a set of capital X i's, is it?
No, sorry, Alvin, could you repeat?
Q naught is a set of sets,
Not
is it?
the set of initial states. So this comes from the automaton. So what are we doing? We are trying to get a formula given the automaton. So it's a translation from the automaton to the logic. So the automaton is of the form as we saw, like it's usually Q sigma Q naught delta alpha, right? So Q naught is the set of initial states, right?
Okay. Mhm.
The set of initial states, and for every state, we are saying that for every state like Q1, Q2, Q3, here we are going to have sets of the form x1, x2, x3, like this, right? So
Mhm.
sir,
yes,
so can we say like Qi belongs to Q naught or like Q naught of Qi whatever? So we could say like there exists an Xi such that Xi of X and Q naught of Qi.
yeah. So let's see. I think so. You were saying there exists a capital Xi.
Capital Xi
Huh?
such that Xi of X, if there exists an X as that first of X implies that part is there.
Yes. So that should yes.
Implies there exists an capital Xi.
Okay. Implies
There exists capital Xi
right.
such that Xi of X
Yeah, but okay, but I also have to say that
and Q naught of Qi. Qi is in Q naught. Can you see that?
no. So the thing is that like, so when I'm constructing the formula will have variables, right? So how do I write the variables? So the variables I'm saying that corresponding to the states, corresponding to the, so essentially like, so when I'm writing, for example, Qi belonging to Q naught, right? So this is like saying, suppose Q naught equal to, let's say, I mean, if I try to expand this part, okay? So if I try to expand this part, actually like Q naught, let's say, let's, for the sake of an example, let's say this is some state Q1, Q4, Q5, right? So then this part will be expanded as like you have x1x. So after the implication, this part I'm writing, right? This part will be either some, this is just a like a compressed form of like x1x or x4x or x5x. That's the thing. So actually in the logic, we don't have something like this. It's just that I'm writing this in a compact form. Okay, so actually, I mean, one should write it in this way. Okay. Yeah. Okay,
So,
so yeah, indeed you should write the quantifiers also, like the quantifiers for the xi's as well, like there exists some x1, x2, x3, all that. But okay, I'm assuming that like yeah, you can write them here and yeah, you can write these sets, and I mean, which anyway we will be writing for some bigger formulas, maybe even starting here and all that, right? Yeah, so that's why I did not, yeah, write these quantifiers here, but essentially, like if I write it in this way, so this is like a compact form for writing this. I mean, this is essentially like I'm trying to say the disjunction is over all these initial steps. Sorry, Shantan, did you have a question?
yeah, so basically, so we somehow need to connect this qi and xi, right? So do we need another operator to do the? Matlab, are you introducing some operator to say that this qi, which are the initial states, these correspond to these xi's, or are we just assuming it that these xi's are the initial states?
No, you are
Matlab,
not assuming anything. So your set of initial states are given, right? Like say you
right.
have an automaton which looks like this.
Yes, yes, yes. I understand that. Hmm.
So you are given an automaton which is like this, and suppose
Hmm.
the initial state is, if the automaton is specified, then you also know what the set of initial states are,
Yes, exactly. Yes.
right? So if you
Hmm.
know what your initial states are, then you can take a disjunction over these initial states, right? The sets correspond
Right.
to these initial states.
Right.
So this is what I'm writing here. Like this is just a compact form
Okay.
for writing this.
Acha. It's just the okay. It's just the way to write this, but it is there. Matlab, we know this. Matlab, from the automata that we have been given, from that we know
From
this
the
already.
automaton, you
Yes.
know what your set Q0 is.
Yes. Yes. Okay. Okay. Got it. Yeah.
So if your Q0 is like Q1, Q4, Q5, the actual formula will look like X1X or X4X or X5X, like that. Okay. Is it clear?
Yes, it's clear. Yes. I was thinking that we need some other operator to link those things, but since the automata is already given, we know this, we know the initial state, so it won't be a problem.
Yeah. So what about the next one? Like for each pair of consecutive positions XY, the sets for X and Y and the later at X describe a valid transition. Right? So you have like it's a set of, I mean, we are trying to define a valid transition. So you have a run, and in the run, like you have the consecutive positions, and then you have to define one. So how would you do that?
You should kind of just encode all the possibilities.
Yeah, all the possible transitions. If you are going from X to Y, like X and Y are like the positions, and Y, let's say, comes immediately after X. So how do you define a transition?
Suppose X,
So first of all, how do you say X and Y are consecutive positions? Sorry,
Next.
next of X, Y, right? And we saw how to define next of X, Y in the logic. It's a derived predicate, but you can define it using the logic, right? So how do you do that? For all X, Y, for every such pair of positions X, Y, such that Y comes after, immediately after. For all X, Y, one can also write for all X, for all Y, but it's okay, such that next of X, Y, what does it imply?
XI,
So it has to be a valid transition.
So, like the xi of x, which is
Mhm.
equal to 1, and the position at x, that, and the final xi of y, this triplet should be a valid triplet. I
Mhm.
don't know how to encode it exactly.
So let's say X the position X is in set, let's say capital Xi, let's say this. And let's say the position Y is in Xj, right? And let's say the letter is A. Let's say the letter is A, right? So now what would you write? So you have Xi of X, you have Xj of Y,
PA of
PA of X. Okay, so you will write Xi of X and PA of X and Xj of Y, and it has to be a valid transition.
you can do or over all the
Exactly.
transitions of the
You can do or over all the transitions QI A, QJ belongs to delta P. Clear? Right? So this is again a short form. This or over QIA, QIA, QJ belonging to delta, it's again a short form, right? You just have to, if you expand this, you will look at all the i's and all the j's, and then you will expand it with all these disjunctions. Clear? Okay. Right? What about the final one?
the eventually thing.
Hmm.
If it is at a good state, then eventually it comes back to the good
Okay.
state.
Where it should also reach some.
Oh, yeah, that works. So,
So this
so
should.
initially it
Ah,
will be eventually it reaches some good state,
ah,
and once it goes there, it comes, there is some good state, the same thing we did earlier.
Hmm.
There is some good state where it eventually comes to that good state, and from that state comes to that good state.
Sure, that's one possibility, but there can be even a simpler way to say this, right?
The
How do you define a Büchi condition? Just how do you define a Büchi condition?
Comes to the good state.
A good state is visited infinitely often.
so
How do you say that a good state appears again, a good state appears again, a good state appears again?
so there exists X such that Xi of X is one of the good states for some I,
Uh-huh,
and
Implies
If-
for y greater than x,
uh-huh,
xi of y
uh-huh.
is valid for all the good states.
Okay.
Or over all the good states, it is like
Okay.
that.
So that's an easy way to say.
Yeah.
I mean, but you can maybe write in other ways also, right? So can you say that again? Like maybe you can tell me the whole formula, what I should write.
There exists x or over all the good states qi belonging to alpha.
Okay, let me write. There exists an X.
That's that.
But
or-
how do you say that it will come infinitely often?
and then you put an and then over.
How do you say
so
infinitely
first
often?
will be like that.
Just say for all x.
For all X, okay.
Yeah. For all x, there is a y greater than x such that it comes there.
Okay, for all X, there exists a Y
Y such
such
that
that
or over all the good states.
X less than Y is greater, and Xi of, let's
Y.
say Y, right? So Y is a good state. This is what you were saying.
Yeah.
Right, and if it is a good state, then you have to say
qi and
Qi belongs to alpha.
Yeah.
Right? So for every position, there exists something which is bigger. For every position, there exists something bigger, right? And this bigger position should be a good state, right? So that's the, if there is an accepting run, this should go true. You have an infinite run, you consider any position, you know that since the good states are visited infinitely often, it will be some good state. Some position will be there, which visits a good state. Good. Right? So essentially then what do we have? we can say that for every NBA, right, we can write an MSO formula phi A that describes all accepting runs of A, right? All accepting runs of A such that L of A equal to L of phi, right? So now if you see, for example, the formula that you have constructed, right? It's essentially like you are interpreting over this word model because you have these positions, like you are saying that X less than Y and so on and so forth, right? It's not only just the word, but you have the entire word model. And we saw that in the word model, you will also have the domain, and the domain is over the positions and things like that. It's the word model which is satisfying the formula, or a set of word models which are satisfying the formula. And then when we are talking about the L of phi A, we are extracting the labels from that positions, right? And that will give you the word exactly, right? So yeah, so we are saying that A accepts W if and only if we have this word model satisfies phi, right? It's a word model because we are looking at those positions. We have the domain with which, I mean, the positions construct the domain, and that's how we are getting the word model, right? So one direction we are done. Now we will start with the other direction, which is from logic to automata. Okay. So, right? Yeah. So how do I do the translation from logic to automaton? So I think we saw this last time that you can look at the formula in terms of a tree. You can look at the formula, given a formula, you can look at this as a tree, right? You have the connectives. And so if you have, let's say, a formula phi 1 and phi 2, you can look at this as a tree like this, right? Okay. If you have a, let's say, a negation of this, then you can consider this as a like a negation, and then there's a phi 2 and so on. Right? So, and then we talked about structural inductions. If you want to prove something on the structure of a tree or on the structure of I mean, some kind of structure, then we can try to prove this for the base cases, which may be in the case of a tree, these are leaves, and then we prove this for the subtrees, right? Inductively. So this is called structural induction. So what we would do when we are given, let's say, a complex logical formula, we say that you can construct an automaton for this logical formula, right? So how would you like to construct such an automaton from the logical formula? How do we apply the structural induction?
Yeah, construct an automata for the subtrees and then you do the conjunction.
Right. And essentially we will be using the fact that the NBWs that we are constructing, they are closed under the Boolean operation. So that is used, that is required, right? If it is not closed under those Boolean operations, then we cannot apply such inductive properties, right? So that closure under Boolean operations is required. Okay. So whatever operators that we have in the logic, so what other things we have other than the Boolean, that combination, Boolean connective, we also had something else. There exists for all. We also have had the quantifier, right? So we also have to show that, for example, like if you have, let's say there exists something, right? X, and then you have a phi1 of x or something, right? So if we can construct a formula for this part, then we should be, sorry, if we can construct an automaton for this part, we should also be able to construct an automaton for the whole formula, right? That is for the uh, when we are applying the quantifier, we should be able to get an automaton, right? So we have to prove all these things. So first, let's do this for the base case. So what were the base cases? So the base cases were like things like if we had something like, let's say, x less than y, right? We had something like this. Then we had a PA of x. So let's see how to construct the automaton for the base cases. Then once we have the automaton for the base cases, we will try to construct an automaton when we have the logical connectives as well as when we have the quantifiers, right? So in order to construct the automaton from the logic, we are first going to simplify the MS. We are going to simplify the MS. So in MSO, we have like two kinds of variables. One is the first order variable, one kind is the first order variable, the other one are the second order variable. Okay. So we are going to have something I call the MSO new, which will have only second order variables. It will have only second order variables. So we are not going to have the first order variables anymore. And we will first say that this logic is actually equivalent to this logic. We are simplifying the logic. How are we simplifying? The first order variables we are going to get rid of. We will be having only second order variables. But then we also need to show that this logic is no less powerful, no more powerful, right? Because we are doing the translation from MSO to monadic second order logic to automata, right? So we are first constructing this MSO new, which will have only simplifying it to have only second order variables, but we should also show that it's equivalent to that original MSO. It's no less expressive, no more expressive, right? So this logic will have this kind of predicates, okay? And we'll show that indeed having this kind of predicates, it doesn't make you more powerful or less powerful. Okay, so how can we express MSO with MSO new? Suppose if I have x equal to y. So before that, so I think these things are clear. X subset of y, it's clear what it means. This is also clear, x subset of PA. Singleton x, this is also something we understand. What about this one, x less than y? What does it mean? It means, so you recall that x is a set of positions, y is a set of positions. X less than y, it means essentially both of them are not empty, and all the positions that appear in capital X should appear before every position that is there in capital Y. Okay, so I'll just write it what the x less than y essentially means. It means that x is not empty, y is not empty, and for each x belonging to capital X, for each y belonging to capital Y, we have that x is less than y. Okay.
This needs to be less than, not be like next to x.
No, it is just that small x, like every position should be less than the every position. So how about x equal to y? So we say that they are equi-expressive, okay, equivalent. So we have to show that whatever we had there in the MSO, they can be expressed with the MSO new. How can you do this? X equal to y. We have these things at our disposal. X is one position, y is one position. How do you do that?
capital X equals capital Y is good. We
But
still have
capital X and capital Y may not be singleton sets.
Singleton X, singleton Y, capital X.
Okay, but
But then
yeah, we have the subset, so we'll just use that. You are right. So we'll say
subset would be neutral. Yes.
singleton X and singleton Y. Y
X subset.
and X subset of Y. Okay. Okay.
But do we have equality in this new system?
Yeah, equality is, you can always assume that it's there. Okay, so even if you say that singleton X and singleton Y and X equal to Y,
It would still.
right? So you don't need to add separately Y subset of X, because if X and Y are both singleton X, then X subset of Y is sufficient, right, to say. Okay, what about X less than Y? It's just now again the same singleton
And X is different.
singleton Y and X less than Y. What about this thing? Y belongs to the set X.
Singleton X and X singleton Y,
Singleton Y
X subset of,
Y
sorry, Y subset of.
and Y is a subset of X. Okay. Similarly, this one is singleton X and X subset of E. Clear? So can you tell me now about the other ones? Expressing MSO mu with MSO. So how do you say X is a subset of, these are very easy and we don't need to write, but I will just, let's see that we are convinced. X subset of Y, we can say X sums.
X implies X.
Sure. Okay. So are you following the online participants? Capital X subset of capital Y. It's like for all X, X of X implies Y of X, right? So this is what X subset of PA singleton X, you can also say singleton X. How would you say this?
There exists an X.
Yeah.
Such that capital X of X and
For all Y,
Y not equal to.
yeah,
So
for all Y such that Y not equal to X implies not of
X.
XY. Right? Okay. Okay. Is it okay? Fine. And X less than Y also you can add. Yeah. For all X such that for all small X
For X.
such that X of for all X
For all X, for
for all Y such that
X of X and
And
Y of Y
Y of Y implies
implies X is.
Y. Okay, good. Okay, so this is, we are convinced then that MSO and MSO mu, they are equally expressive. Right. So now we construct the automaton for each of them. So how do you construct the automaton for this X subset of Y? So how will the alphabet now look like? So you can have, let's say, multiple sets. So you can have different free variables, right? And we saw this extended alphabet. We saw this extended alphabet, like you have X1, X2, X3. So let's say at the top we had the letters, correct? So if you recall, we had something like this. So you can say that in the beginning, at the top, we have the letters, and then we had this X1, X2, X3 like that. Okay, so if we want to do something like this, so just if I show you the first one, you'll be able to do for the remaining ones. So I'll have, so what are the what are the labels here on this transition? I have sharp here stands for some letter. It can be some letter. We are talking about these, the positions here, right? So, and let's say the first position here stands for capital X, then the capital Y, and maybe following that there may be some other sets. Okay. So whenever there is a 1 here, then there has to be a 1 here, and then there can be something else, right? What else can be there? So this is one possibility. 0, 1 is also possibility.
What is hash standing for?
The hash stands for any letter, that's all. Okay, so the hash stands for a letter in sigma. Okay, and star denotes a bit vector in 0, 1, n minus 2, where n is the number of free variables, right? That xi is clear. What else is possible? 0, 0, right? So these are the things. What about X subset of PA? Now you can tell me. What are the things which are possible?
Instead of hash, it will be A.
If it is a hash, then what it will be? Can it
If
be?
it's hash not equal to A, then it
Ha.
has to be 0.
Right. But for anything arbitrary, okay, it can be 0 is fine,
Okay, fine.
right? And if I say an A,
A,
then
one.
it has to be a 1. Clear? Okay. Good. What about singleton X? So you are saying now that for this set X, a 1 should appear, right? Before that, if you don't see a 1, then you should be in a non-accepting state. Once you see the 1, then you will reach an accepting state. So this automaton should have 2 states. The one that we are going to do.
I'm not following the notation.
Okay, so sure. So okay, so when I'm reading something, what do I usually, how does the alphabet or how does the transition look like? Like if you are, suppose you have an automaton, right? In general, when you have an automaton like this, you put an A or something, right? And now we say that you have some n free variables. Okay. Now corresponding to those n free variables, right? So we are going to have the alphabet itself will be a column of size n plus 1, where the first row in that column is this letter, and the next n such things, it will talk about the sets x1 to xn, right? The next n rows correspond to the sets x1 to xn, right? So now I am saying that when I'm drawing the automaton corresponding to x subset of y, so this one, the hash, the sharp here corresponds to some letter, some arbitrary letter. It can be any letter, okay? And I'm saying that this second row corresponds to x. The second row corresponds to x here. The third row corresponds to y. And here the star is the corresponds to the remaining n minus 2 that rows. We don't really need to talk about that when we are just talking about x.
So X is primarily the entire second row after we.
Correct.
Okay.
Yeah. Right. Okay. In a run, it will be like this. But in order to, like, if I just want to say how the automaton, so what are we doing? We are trying to construct. We are going in this direction, logic to automaton, right? And how are we doing that? Using structural induction. So we are saying that construct automaton for a simple formula and then build them up to get the whole automaton.
Yeah.
You may have a big formula, right? And I'm saying that identify the small parts, the base cases of that formula, construct automaton for these base cases, and then for the whole thing, we'll try to apply that Boolean connectives, the quantifiers, and we'll construct automaton for that.
Okay.
Okay. Now we are constructing the automaton for the automata for the base cases, for the individual base cases.
Okay.
So what were our base cases? So the base cases were these things, right? So these are our base cases. Okay. We are constructing automaton for each of them. We are constructing, right? So first we started with this case, X subset of Y. Okay. So this is the first, this is in the first row is the letter here, and then I have the X and I have the Y. So now if you have such transitions, so what are the labels of these transitions? The labels means what is the letter corresponding to the transition. Now here the letter itself is of the form sigma cross 0, 1, n. The letter itself is an element from this set, right? Because this corresponds to all the free variables, and this is the actual letter which comes from the sigma.
Yeah.
Right? So this is what we are doing. Now I'm saying that out of these n such free variables, let's say the first two free variables, they are X and Y. Okay, I mean, it is just for our convenience. I mean, you could have put the X somewhere, the Y also could have been somewhere else in that n rows, right?
Yeah.
Correct. So here, suppose this is my X, this is my Y. Now, is it clear like why I say that if let's say this is 1, then this has to be 1,
Yeah.
right? Because X is a subset of Y. If you have a position which belongs to X, then that position also has to belong to Y. So that is denoted by the 1 and the 1. Correct?
Yeah.
Then similarly, I'm saying that if this is 0, 0, 1 is also a valid thing, right? Some element is not in X, but it is in Y. 0, 0 is also a valid thing. So all these are valid labels or valid letters for this transition. Like when I say letter, I'm saying that this is the n plus 1 cross n plus 1, that column itself, the whole column.
Okay.
Right? So all these three are possible. Three things are possible. Okay. So actually these are like, maybe you can consider this as three different transitions, but I'm just like the way you often write, right? Like you have A comma B. So it's like that.
So these vectors are the alphabets in the new language.
These vectors are the elements of the alphabet in the new automaton. Okay. Clear? Similarly, is it clear why I have X subset of PA? Why do I have this?
Yeah.
Right? Because if you have an A, if an A is coming, then that position which is marked with an A, that position should belong to X, right? Because X is a subset of PA.
Shouldn't be other way around. If
So-
there is a X, then there should be a corresponding to it.
Sorry,
Like
if
if the X slot is 1, then the alphabet slot should be A. But
so what does it mean again? So it means that if I see a 1,
then
if I see a 1, then the letter here should be an A.
Yeah.
If I see a 0 here, that means this is the position X here again, right? So this is the letter, this is X.
then it can be anything.
Then it can be anything.
Yeah.
Even if it is A, it can still be 0.
Yeah.
Right? So that's what it means. Now, do you have a question?
No.
Okay. What about singleton X? So what about singleton X? So the idea should be that I should be able to see one position that belongs to X, and only then I can reach the final state of the automaton. The final state means like a good state of the automaton, right?
So if I see a zero in the X slot, I'll stay in the first state.
Right.
If I see a one, I will
So
transition.
if I see something like hash 0 star,
Yeah.
I stay here. If I see a hash 1 star, then I go from this step to this step, right? From this step to this step.
And
And
now
here, yeah,
It should only be hash zero.
has zero.
it should only be a hash 0.
Yeah.
Right, very good. So here again, I should have only hash 0 star. Yes. Clear? What about this one, x less than y?
See, Basi, one question, isn't PA itself a set?
PA itself is a set, exactly.
And that always,
And PA corresponds to, like, it's not a free variable, right? So we don't have a row corresponding to the PA, but it denotes all the positions where you have seen an A. Right? PA is denoted by all those positions where you see an A. So whenever there is an A, that kind of corresponds to the set P, those set of positions. It's not a free variable.
okay. Mhm.
Right? It's kind of fixed in your this thing. Right? And I don't need to put a separate assignment. I don't need to put a separate assignment for this. It's already fixed by this.
By the word itself.
By the word
model.
Exactly. Okay. Yeah. Right.
So I have one question. So
Yes.
so we are converting from this logic to this automata, right? So once we so given a logical formula, we are trying to convert our automata from that. So once the formula is given, how can we understand that it is a PA? Matlab, yeah. How can like so? How can you distinguish between if it is an capital X or if it is a it's a PA?
No. So it is like I am constructing from the logic, I am constructing the automaton. Right?
Right,
Right. So I'm saying
right.
my logic has this thing, X subset of Y. Correct? X subset of Y. My
Right.
automaton should look like this. That's all I'm saying. When I'm
Yes.
when I'm constructing an automaton from the logic, given the logic formula like this, my automaton should look like this. That's all I'm saying.
Right. So how can we say how can we distinguish that this y is a y, matlab x is a subset of y and x is a subset of PA.
How
The-
do I know that? How do I
Yes.
know that?
That x is a subset of y and x is a subset of PA. Matlab, how can you distinguish between this y and PA?
No, I mean, I'm not distinguishing anything. It's not like the word is given. I am given only a formula. Okay, I am given only a formula. The formula will have such a thing. Let's say I'm given such a formula. X is a subset of Y or X is a subset of PA. I am not distinguishing between them. I am just given such a formula, or it may be a small part of a bigger formula. Okay, and I don't know, for example, let's say Y and PA, how they are related, I don't know. All I'm saying that if I have to construct an automaton corresponding to this, or if I have to construct an automaton corresponding to this is how they will look like respectively. The automaton corresponding to X subset of Y will look like this. The automaton corresponding to X subset of PA will look like this. These are my possible transitions. That's all. That is all I'm saying.
No, I think what he's asking is whether we treat Y and PA analogously or are they like, is there a difference in how we treat Y and PA?
So, well, I mean, the thing is that the PA is automatically, it comes from this A. I mean, if I wanted, I could have as well had a different row here for PA. Suppose all I'm saying is that I could have had like a separate thing sharp, let's say X, and I could have had a PA here, right, separately. But the thing is that I don't need it because this thing is already, it already comes from this A. Whenever there is an A here, I know that this, for the set PA, there is a 1 here. So I don't need that separately. Does it make sense?
Kind of. So maybe if we construct an example, maybe at that time it will be clear.
Okay, so I mean here itself we are constructing like the automation itself. Like what I'm saying is that given this formula, we are constructing the example. I mean, this is the example of the automaton for this formula.
Right. Right.
I mean,
No,
see,
these I'm getting. So how this automata is being constructed, I'm getting it.
right.
Why X is a subset of PA has this kind of matlab, for X is a subset of PA. For that, the automata will be this, and the transitions will be this. This I'm getting.
Mhm,
But my main what I'm not getting is that given some arbitrary formula,
mhm.
how like
So,
at that time when we'll construct an automata, at that time how it will look like and
sure. Okay. So let's say I have a formula like this. Okay, for all x, there exists a y such that x less than y and p1 of y. Okay.
right.
So this says that this is the language which corresponds to, there are infinitely many ones, right? This corresponds to this formula corresponds to this particular language, right? We saw this in the last class, correct?
Yes,
Yeah. So this you are convinced that this is the formula. Now I'm
yes,
that given this formula, suppose you want to construct an automaton. How would you construct? First of all, like this formula has some free variables here, right? Like we have this x less than, sorry, it doesn't have any free variables. So we have this x less than y. So this is like an MSO formula. This is an MSO formula. Clear? So now given this MSO formula, what we'll do is like, we'll construct an MSO new formula, which will be equivalent. Okay, right? So corresponding to the small x, we will have a capital X, right? Which will say that singleton x, okay? And then corresponding to y, we will have a capital Y, which will say singleton y, okay? And we saw this x less than y. How do we express x less than y? We said singleton x and singleton y and x less than y. Singleton x and singleton y and x less than y, capital X less than capital Y, right? And we also have P1 of y. So we said, how do I have P1 of y? It was like singleton y and y subset of P1, correct? So this is what we would have. So essentially we are constructing this MSO formula to an MSO new formula, right? And now for each of these things, like for this thing, we can construct a formula, right? We can construct a formula for this thing. We can construct a formula for, sorry, we can construct an automaton for this. We can construct an automaton for this. This is what we are seeing now. And then for the conjunction here, also we can construct an automaton, which we'll see how to construct an automaton. And the final thing that we get right? The final thing that we will get, we also have some quantifiers here, which we'll see how to add the quantifiers. And then the final thing that we get will be the corresponding automaton.
Okay, okay. Now I
Okay.
get it. Yes, yes.
So we are constructing automaton for each of these small things. Like we have the automaton for a small formula like this. We have an automaton for a small formula like this. Then we will have an automaton for the conjunction of these two things. And then we will also have an automaton when we put the quantifiers. Right? We will have another automaton which will have the quantifiers, and that will finally have the automaton, the final automaton for this whole formula. Okay, so that's the thing. Okay, good. So okay. So yeah, so this part is clear. Now what about x less than y? So let's do this thing. So I need to have something like at some point of time, I'm going to see some element which is here, some element which is in this set. And I cannot see any more elements from the first set, right? So this is the thing. So let's say I see something like sharp and a 0 and a 1 and a star like this, okay? And then I cannot see any more elements from the first set. So I'm always going to see a 0 here corresponding to the first set. I say what this question denotes, and this term. So the question essentially denotes either 0 or 1. Okay, so the question stands for a 0 or a 1. Okay, and here also, what shall I have?
Question 0. Hash question 0.
Hash question 0 star. So this says that I will keep seeing 0 for the y for this element. The moment I see a 1, that means some element here, then I cannot see any more some element in the first set, in the X set. Right?
Sir, but here y can still be empty.
Yeah, the first state should also be an accepting state.
No, then it will accept everything. Because it would just
No. I think I say this. X less than y.
We could just put
See x less than y, x and y are non-empty. Okay, x and y are non-empty, and for each x you have this thing. But you are right in one way, because somehow I'm not saying somewhere that x has to be non-empty, right? This is not quite captured here. So it will require some small changes, which you can possibly figure out how to do. So if I have to say x is non-empty, then somewhere I have to say that there should be a 1 that should come.
I think we should add another.
You should maybe add another state. Yeah, something like that. Okay. But pretty much you got the idea that I'm not getting into the details. You can figure out that's a corner case. Yeah. Is it clear to all the online participants now what we did? So we covered all the base cases, the automaton corresponding to all the base cases. Any question from the online participants about how we constructed these automata? Okay. So now we should have for Boolean connectives. So what are the Boolean connectives we would need? Like we have, for example, implications. We have by implication. We can have, let's say, conjunction, disjunction, negation. But one thing I would just like to add, have you seen something called this set of functionally complete operators? Functionally complete operators.
Not and then.
Not and or should suffice. Okay. Okay. So not and or should. Yeah, and maybe another one, right? So these are the functionally complete. It means that you can get your entire, the other Boolean connectives using just this set of operators. So we will have this set here, not and or. Okay, so this is functionally complete. So everything else we can get using not and or. So we know that NBW are closed under complementation. We have seen that, right? We have seen that, like, given an NBW, you can construct another NBW of size 2 raised to n log n, right? So given an atomic formula, I'm just writing this, given an atomic formula, or given, atomic formula for phi and psi. So this is a psi, we can build automata for not phi and phi or psi, and hence for all Boolean combinations of phi and psi. Is it clear? Since the negation and the disjunction, that is functionally complete, we can construct automata for all Boolean combinations of phi and psi. Okay, and we also, why can we build automata for not phi and phi or psi? Because NBW are closed under negation as well as they're closed under disjunction. Okay, so now if you look at phi and psi, right? If you look at, say, phi and psi, so phi can have a set of free variables, psi can have some other set of free variables. Now, if I look at the overall formula, say, let's say it's like this, phi of x1 to xm and psi of y1 or psi of y1 to yn. So how will the alphabet look like for this formula? How will the alphabet look like? How many columns, how many rows will be there?
For phi, it will be n plus.
For phi, it will be n plus 1. For psi, it will be n plus 1. And when I have phi or psi,
Plus
n plus 1.
Because
the first A is the same, right? So n plus 1.
Yeah.
Okay. So the alphabet will have n plus 1 columns. I mean, the letters in the elements in the alphabet will have n plus 1 columns. Oh, sorry, rows. Okay. Good. So now, what is left? The final thing that is left is the quantifier. Right? We have to see how to get the quantifier. Okay. So consider phi of this form, and psi has x2 to xm. Right? So what are the free variables here? X1 to xm, and here the free variables are x2 to xm, where the psi is of the form there exists x1 phi x1 to xm. Right? So x1 gets bound here. X1 gets bound here. So the psi has m minus 1 free variables, and the phi has n free variables. Correct? Now, let's say corresponding to this, I have an automaton which is of the form like q sigma phi qy f delta, and here I am saying that I have the same set of states, everything remains the same. Where will the change be in terms of the alphabet? Now there will be n rows here there will be n plus 1 rows, right? And there is a delta prime, the transition will change. So psi again is like of this form, there exists x1 phi, and right. So as I said that here there are n rows, here there are n plus 1 rows. And now let's see how the transitions look like in this delta and the delta prime. Okay, so let's say I have a transition I'm talking about. I'm looking for a transition in this delta prime. So how will it look like? Suppose you have QA x bar. X bar I'm writing because it's like a vector of things. Okay, and or I may write it slightly x, capital X bar. I'll put a transpose here because it's like a column, and Q prime, it belongs to delta prime if and only if. So I'm now saying that we would have this, right? And so given this, so I'm already given the automaton, this automaton. I'm trying to define this automaton, right? Which has this additional existential quantifier. Correct? So that means I had the transitions with n plus 1 rows, the transitions, the letters had, each letter had actually n plus 1 rows. And now I have to just get rid of one such row, right? I have to get rid of one such row. And so how will that be the case? So yeah, right. So I'm constructing this. I'm given this. Here I'm given this, and I'm constructing the automaton. So I'm given the automaton A5, I'm constructing the automaton A psi. Okay, so I'm looking at, so I'm having a transition here. And when will it be the case? So it will be like I have another extra something like this, x bar, transition Q prime belongs to delta, or I have A1 x bar transition Q prime belongs to delta.
So this is just eliminating the rows, not the-
It's just like eliminating the row. So this is what you do, right? You have this additional quantifier which binds one of these variables. So earlier you had so many free variables, now you have one less free variable. So what is this automaton then doing? What is this automaton doing? This is kind of guessing a value for x1 and taking a transition. Okay, it's guessing a value. It's guessing a value. So this transition here, it guesses a value of x1, which can be either 0 or 1. Okay, and so essentially I'll say that the automaton A psi, it guesses a value of the x1 component, value of x1 component at every step. Is it clear? Okay. Now I'll say that there is an accepting run, which is of the form this. See, Q1, let's say A1, X1 bar transpose Q2, A2, X2 bar transpose like this, if and only if there is an accepting run say A1, B1, X1 bar, transpose Q2, A2, B2, X2 bar, transpose, so on. So this is a run in which automaton? So this is a run in that A psi, okay, accepting run of A psi automaton, if and only if there is an accepting run like this in the A phi automaton. Okay. So the A psi automaton, it is having a run, and that run at every step, it guesses a value for that x1 component. Okay. So that's how you are eliminating a free variable. Okay. So this is like a, I mean, when we have this additional quantifier, this is how we are constructing the automaton. Okay. So we have seen that using this structural induction. So the base case we saw, then we saw the inductive cases, which means for adding the Boolean connectives as well as for adding the quantifiers, how we can construct the automaton step by step. Okay, and this is how, given any formula, you can split the formula into small subformulas, get the automaton for the small subformulas which are the base cases, and then given the formula, you can build the tree, and then you can construct the automaton. The MBW are closed under exists and for all, right? Sorry, exists and the negation, and you can construct the automaton, and for the quantifiers also you can construct the MBW in this way, and thus you can get an MBW for the entire formula, right? So the closure properties are important here. Now there is a question. So suppose I give you an arbitrary such formula. I give you an arbitrary formula in MSO, monadic second order logic, right? What is the size of the automaton? And secondly, you can also think of the other direction, which we saw in the saw previously. Given an automaton, what should be the size of the formula that is being constructed? We saw both the directions, automaton to logic, logic to automaton. So given an automaton, what is the size of the logical formula? Given a logical formula, arbitrary logical formula, okay, what should be the size of the automaton? So do you have any thoughts on that? Anybody like?
By size of the logical formula, you mean the number of connectives or
The number of connectives plus, let's say, the number of variables, right? Yeah, I mean, the number of connectives is a good measure. Yeah, let's say.
Only the not part will cause a blow up. Other parts won't cause a blow up.
The not part will cause a blow up. How much blow up the not part can? Exponential.
But then the sub parts could just be like 1 state, 2 state. So, but it could be exponential.
It could be exponential. The not part can cause an exponential blow up. How many times that exponential blow up can occur?
The number of not really, but yeah, it can.
It can, not really.
It can.
So what is the thing?
Like, because it depends on how much the scope of the knot is. Depending on that, the number of states, it will cause exponential for that number of states.
So suppose you have a knot of something like this. Okay. Suppose, so I told Vishal that I will be starting doing the alternating automated today, but I could not start it, sorry, but I think, yeah, but next time we are going to start with that. So suppose you have something like this, knot of phi1 and knot of phi2 and knot of phi3 and like this, okay?
We are using the fact that
so what will be the blow up if you have such a thing?
We need to first translate all of this to ours, not an ours.
So you see that we are also saying that we are constructing for exists, right? You can also have a for all. So the for all can be translated to like it is not the case that for all
That's
phi,
not it.
not the case that there exists negation of phi, right? It is not the case that there exists not of phi, right? So if you have for all, this they can also kind of like give rise to such negations in the formula. So let's say if you have a formula of this form like negations and so on, what will be the blow up?
Exponentially big.
Not necessarily, no, because not of not will again be the original one. So if we somehow smartly do it, we can avoid.
Good, but what if you have a for all there exists? So something like a formula which is of the form for all there exists, then a for all then there exists, and so on and so forth.
That might mess up things. If there's no for all there exists, I think it shouldn't be double exponential. Like in exponential, it should be.
It could possibly become that.
Why double exponential?
No, like negation exponential, and if you again negate it, it blows up. But that's not necessary because we know the original.
No, my question is that why not triple exponential?
Formula.
Okay, yeah, we just went above exponential.
Exponential to exponential.
Can you go above triple, or can you have like a tower?
Yeah, I think it will become a
It will become a tower, right?
Mm.
And in fact, like you can
construct.
construct a family which will show such lower bounds, which will not cover, but that can again be like a seminar topic. But I have already thought of a few seminar topics, but yeah, but that's the thing. Like you can show that this is inevitable, like in the sense that you can construct such families where the blow up from the logic to automata part, it can be a tower of such exponentials.
Okay.
Okay, good. So we'll then end here. So anybody has any question, and then so next time we are going to start with the alternating automaton. I thought I would start, but I could not. So I'll end here. And anyone has any question with this? So we completed the proof of the Büchi's theorem, right? So we looked at monadic second order logic, and it's a characterization for omega regular languages. So what are omega regular languages? These are languages which can be accepted by MBW, and also we can say that these are languages which can be characterized by formulas in MSO over words. Okay, anybody has any question? So
that MSO new, is it same, like, is it equivalent to MSO in what it can express?
exactly. So that's what we showed, right? We showed that indeed that MSO new, where we are getting rid of all the first order variables. So we will only deal with second order variables just to simplify further, because we don't want to have two kinds of things like the first order variables as well as the second order variables, which might make our life a bit more difficult. Instead of that, we say that we would only deal with one kind of variables, which are the second order variables. So that is what we are calling MSO new. And we added some additional predicates here. Okay. And we saw that these additional predicates doesn't add to the expressiveness, or it doesn't become more powerful, because these things can be expressed with MSO as well as MSO can be expressed with MSO. Does that answer your question?
Yeah.
Right?
It's just for a like a intermediate convenience stuff.
Yeah, it's just for convenience. It's just for convenience. Okay.
I still have a question. So can you go back to the place where you constructed the from the logical formula you constructed the automata.
Yes.
Not this, the thing that you were showing before, like
Uh,
the
oh,
example one.
okay. So,
Just
yes,
before.
yes.
Yes, this
Ex-
one, right? So, in the MSO formula, we have x, y, and this predicate p1 also. We know that it represents something like p1 of y. So, one second, just let me think.
So first of all, this is just a first order formula, but yeah, it's also an MSO formula.
Yes, yes, right.
Right? And
Okay, one second. Okay. So, okay. Here is my question. So, suppose this. So we know this. Currently, we know that this P1 represents something like yes.
so P1,
So
why we know that it can be expressed in this way, right? And
right.
correct. And this we can have a formula corresponding to this. Right? We saw
Yes.
how to construct an automaton corresponding to this.
Yes.
We
Yes.
saw
Yes.
how to construct an automaton corresponding to this. We saw how
Yes.
to construct automaton corresponding to the conjunction of two
Conjunctions also. Yes.
formulas. That also we saw.
Right. Right. I see. Okay. Just a minute.
Right? Because we exactly did not see the conjunction. We say it like, okay, if you have negation and disjunction, then you can also do it for conjunction.
Yes, right. That is all fine. That is all fine. Yeah. The confusion I'm having is that suppose we didn't know that this P1 is this P1, matlab,
Huh.
right?
So you don't have to know. The word doesn't come here. You are not given this word to start with. You are only given such a formula. Now you see that which all words will satisfy such a formula. You are just seeing this. Which all words will satisfy such a formula. You just, for example, look at this formula, singleton x. Okay. If you look at such a formula, just a singleton x, then what are the words which will satisfy this formula? You just look at this automaton and see what are the words which are there here. Like you have a 0, then followed by some number of zeros, followed by some 1 and some zeros again. Okay, forget the star part. So just see sharp 0, then some number of times, sharp 1 and sharp 0. Right? So it is like sharp 0 star, then sharp 1 and then sharp 0 omega, right? So this is the set of words, right? Like I say set of words because star can denote any number of any finite number of such occurrence of sharp zeros. Now these are the set of words which will exactly satisfy this formula. Clear?
Okay.
So similarly, if you are given with some formula, you will get the NBW will give you a set of words which will satisfy the formula. Right? For example, for this simple formula, this is your set of words which will satisfy the formula.
Okay.
Yeah, so if you just take now this particular formula yourself, right, and try to draw the whole automaton by using the gadgets we saw, right, by using the automata for the base cases, if you draw the automaton for this entire thing, you will be able to see now how the automaton looks like. Okay, and you will see that the automaton will accept only those words which satisfy this formula. Clear? And that will be exactly this set of words.
Okay.
Okay. So shall we then conclude here?
Yes.
Yeah, so if you have questions, just you can send me emails, or there are this on the group on the this forum that we have, the classroom. Like you can also add your post things there, right? I mean, it would be good. In fact, like if we have more discussion. I mean, we used to have more discussions in the last time I offered this course. In fact, like many students used to post questions and discussions on this kind of things. But yeah, we should have them. So I'll just finish here, and we are going to start something called alternating automaton on Monday. So that will be so today is Monday, right? So Friday, yeah. So Friday at 9:30. Okay. Okay. I'll then just stop the recording.